A survey of machine learning applications in functional verification. Abstract: functional verification is computationally and data-intensive by nature, making it a natural target of machine learning application. This paper provides a comprehensive and up-to-date analysis of the functional verification problems addressable by machine learning (ML). Among the various ML techniques and algorithms, several emerging ones have demonstrated outstanding potential in functional verification. Despite the promising research result, the paper identified critical challenges of applying the ML in the industrial EDA environment. Finally, the authors indicate that the unavailability of high-quality verification data is impeding the research of ML in functional verification and calling for a contribution to open verification datasets. Introduction. Ever-increasing design complexity and shortening design-to-market time has demanded faster and more accurate functional verification. Industry surveys indicate that design engineers spend about half of their time on functional verification, and the situation has not improved over the years. So by its nature, functional verification is computation and data intensive, which makes it an ideal field to apply machine learning (ML) techniques in EDA. ML development was witnesses exponential growth in past decades. An abundance of the ML techniques has been devised to address challenges in data analytics of every data modality, including numbers, text, audio, image, video, graph, and a combination of the multiple modalities. Depending on the data label's availability and the problem's nature, supervised, unsupervised, semi-supervised, or reinforced learning can be applied to analyze the data. Many ML algorithms were also developed for these data analysis tasks, including the regression, instance-based, and regularization, decision tree, and Bayesian support vector machine (SVM), and artificial neural network (ANN), and deep learning and dimensionality reduction, and many more emerging algorithms. Many ML algorithms have been experimented with different areas of functional verification with various degrees of success. This paper contributes to the overall study of applying the ML to FV by identifying the problems addressable by ML, listing the new techniques and algorithms that are applicable algorithms, outlining the industrial perspective, and discussing the challenges of data unavailability. Section 2 is topics on ML in functional verification. This paper outlines the important topics ML applies to in functional verification. The several existing publications have offered perspective on general problems landscape. Han, Guyu et al. Gives a general overview of ML applications in EDA with limited coverage on verification about the test set, redundancy reduction, and test complexity reduction. Additionally, Ismail and Abdul Ghani provide insight into the automation of troubleshooting, automation of former engine selection, and root cause analysis (RCA), and environment modeling. In addition to the selected topics mentioned above, Kritos Kristetsku also presents the topic of automated code generation. This paper gathers a comprehensive list of ML topics applicable to functional verification, when including all functional verification topics in the general perspective of problem code verification. Table 1 summarizes the topics and subtopics and includes a column for related section, which follow the table. Italicized the text to indicate subtopics that were explored in other general survey publication. Table 1. The topics of ML application in functional verification. Requirement engineering, code generation from requirement specs into the constraint NL text, natural language text, code comprehension, summarization, and translation to the natural language, specification mining from runtime traces, the static code analysis, code smell detection and code quality assessment, automated refactoring, automatic correction, code completion and semantic code search, the verification acceleration, automated selection of formal prover, automated simulation parallelization, complex module approximation with ML models, coverage closure, ML guided random test generation, test complexity reduction, bug detection and localization, assisted root cause analysis, and automated troubleshooting. So, in one, requirement engineering. Requirement engineering in functional verification is the process of defining, documenting, and maintaining the verification requirements, which is critical to ensure the excellent quality of the underlying IC design. 1.1 set requirement definition. Requirement definition involved translating ambiguous natural language verification objectives into verification specs with formality and precision. The quality of a translation directly dictates the correctness of the verification. Traditionally, this process is laborious and consumes substantial design cycles with several iterations of manual proofing to ensure quality. The groups of classic approaches have been proposed to automate translation. One group of approaches is to introduce constrained natural language, CNL, to formalize the specification drafting, followed by a template-based translation engine. This approach requires significant upfront investment in developing a powerful CNL syntax and comprehensive compile and template system to ensure it is powerful enough to address most of the requirements encountered in functional verification. Furthermore, it burdens developers with running an additional language, which prevented the idea from becoming widely accepted. The other group leverages the classic natural language process, NLP, to parse NL specification and extract relevant key element to formulate a formal specification represented in reference 10. The advance of the ML translation in an natural language NL domain has made fully automated machine translation commercially feasible and sometimes exceeds the performance of average human translator. It has kindled the hope of leveraging large-scale trained NL models with up to billions of parameters to directly translate the NL specification to verification specs in the system value assertion (SVA), properties specification language (PSL), and other languages. Several attempts to do a successful end-to-end simulation have been observed, but none have been made production-ready. This major hurdle to this approach is scarcity of available training datasets that pair NLP specification with their formal translation. The most extensive datasets are merely about 100 sentence pairs. The number of pairs in comparison to their NL peers, which routinely come in millions of and even billions of sentence pairs. 1.2 Code summarization and translation to NL. Converts to requirement definition. Summarization looks at the code and translates into a human understandable NL summary. It assists developers in reading less ideally maintained code and understanding complex logic. An ideal implemented code summarization can insert inline documentation into blocks or generate separate documentation with each help the maintainability and the documentation of the code can be significantly improved. The application of the ML on code summarization has been experimented with more popular computer languages, Python and JavaScript. Several groups of approaches have been implemented with various degrees of success. The information retrieval IR based on approaches focused on applying the NLP to source code and looking for similar code with existing summarization in place. This group of approaches heavily relies on the quality of the existing code with summarizes. Its use is only possible within a close organization where many existing code repositories are readily available. Heuristic-based approach instead of try to define specific rules based on the heuristic identified in a module definition. For example, a module with many sub-modules of a basic read and write command lines might be considered in a set memory module. Therefore, the summary can be constructed from a predefined pattern for memory module. At the time of this writing, code summarization in IC design verification has not yet been reported in any literature, so it is reasonable to optimistic that a success of other languages can be realized IC designs and verification, which has not yet to be confirmed by the research community. In particular, recent progress with the cross-language models might help transfer learned knowledge from other languages to the ICDI. However, in addition to the technology general to the ML on the code summarization, the intrinsic temporal parallelism in IC design and verification code can present challenges uncommon in other programming languages. 1.3 Specification mining. Specification mining, as described as Darmeyer, Valentin et al. And Wenchow, Florin, and Sechia, has been a long-term software engineering topic. As an alternative to manually drafting specifications, it extracts specification indirectly from the design under task DUT execution. ML can be applied to mine recording the patterns from simulation traces. It can help automate either the simulation-based coverage closure or formal verification, so it is assumed that commonly recording the patterns might be an expected behavior of DUT. Alternatively, an event pattern rarely occurs in the traces can be regarded as an abnormality, therefore it can be used for diagnostic and debugging purposes. The ML has been applied to pattern discovery and abnormality detection across many domains where temporal data of a complex system are available. Jim et al. Propose a general software engineering approach where the ML is used to discover formal verification from the observing the protocol traces and finding the possible grammatically implementation of the protocol. Successful experiment cited in the paper has been inspired interesting follow-up research project in specification mining with ML. 2 is static code analysis. As the cost of the fixing a bug grow exponentially along the stage of the IC development, static code analysis offers an attractive option to improve code quality and maintainability at an earlier stage of design development. So the 2.1, the code 2.1, the code smell detection and quality assessment. Code smell refers to suboptimal design patterns in source code, which might be syntactically and semantically correct, but violate best practice and can lead to poor code maintainability. A particular example is code duplication, where the same function is implemented multiple times across the project or the entire code base. Some copies can have a particular bug fixed in a relatively short period, while the same bug goes unnoticed to the other copies. So the classic code smell detection relies on a defined heuristic rules to identify patterns in the source code. Instead of manually developing these rules and metrics and the static code analysis tools, and an ML-based approach can be trained on a large amount of available source code to identify the code smells. Research detailed by the Fontana et al. And Anish Chen et al. Have proven the smell detection where the ML can read the universal code smell detection and significantly fewer pattern implementation efforts. The smell score can be used for the code quality assessment and help developers improve the production quality consistently. Furthermore, ML-based code refactoring might provide helpful hints on improving the code smell and even further some candidate changes. The application of the ML in FE is not yet viable, and the unavailability of the large training datasets have prevented existing research from fully exploiting these solutions' potential. 2.2 is coding assistance. The developers working IC design can be most productive when the proper tools are provided. Simple code compilation is a standard frame feature in the modern integrated development environment (IDE). However, the more advanced techniques involving deep learning was proposed and are maturing quickly. It's now possible to train ANNs with billions of parameters from many large-scale open-source code repositories to give reasonable recommendations of the code simply from the developer's implementation intent or the context. So the ML might help IC developers stay productive with systematic code research, which allows retrieving the relevant code by ML queries. As code is usually full of various abbreviations and technical jargon, and semantic searches can be more effective in finding relevant code snippets without correctly spelling the key variable, function, or module names. While similar to semantic search in many existing search engines, semantic code search is able to help find abbreviations and highly technical code with a vague concept. The mean reciprocal rank of the best model evaluated can already achieve usable scores of 30%. Although theoretically the same ML techniques applied to other languages can be applied to IC design, no research has been published yet on coding assistance. 3. Verification acceleration. The survey one indicated the functional verification is still the most time-consuming step in IC design, and functional verification, functional and logic errors are the most important cause of spin. Any improvement in the speed of the FE will significantly impact the quality of the productivity of the IC design. So ML being used for both formal and simulation-based verification for their acceleration. 3.1 is the formal verification. Formal verification uses formal mathematical algorithms to prove the correctness of the design. Modern formal verification orchestration employs formal algorithms to target designs of different sizes, type, and complexity. So the experience and heuristic can help developers select the most appropriate algorithms from the library for specific problems. As a statistical method, ML cannot directly address the formal verification problems. However, it's been proven to be very helpful for formal orchestration. With its prediction of computing resources and a probability of solving a problem, it's possible to schedule formal solvers to best use these resources to shorten the verification time. By first scheduling and multi-premising the solvers with a lower compute resource consumption, the AdaBoost decision tree-based classifiers can improve the ratio of the solved instances of the baseline orchestration from 95% to 97% with an average speedup of 1.85. The other experiment in reference 25, is able to predict the resource requirement of the formal verification with 32 average error. It iteratively applied feature engineering to carefully select the features from DUT, the properties and a formal constraint, which are then used to train multiple linear regression models for resource requirement prediction. 3.2 Simulation-based verification. Contrary to formal verification, simulation-based verification usually cannot ensure the complete correctness in the design. Instead, the design is put under a test bench with a certain random or fixed pattern input stimuli applied, while the outputs are compared to the reference output of the derivative to verify if the design's behavior is reflected. While the simulation is the bread or butter of functional verification, simulation-based verification can also suffer from long verification times. It's not uncommon for verification of a complex design to take weeks to complete. So, a promising idea being discussed in an experiment with ease to use of ML to model and predict the behavior of a complex system. The universal approximation theorem proved the multi-layer perceptron (MLP) on feed-forward ANN with at least one hidden layer can approximate any continuous function with arbitrary accuracy, whereas normalized recurrent neural network RNNs and a specification form of ANN are improved to approximate any domestic system with memory. Advanced ML accelerator hardware has made it possible that ANNs can model the behavior of some IC design modules to accelerate their simulations. So significant acceleration may be achieved depending on the capability of AI accelerator and the complexity of ML models. 4 is test generation coverage closure. Besides manually defined test pattern, standard techniques employed in simulator-based verification include random test generation and graph-based intelligence test automation due to the long-tail nature of coverage closure. Even a tiny efficiency improvement can easily result in a significantly reduced simulation time. Much research on the application of ML to FV functional verification has focused on this area. Extensive ML studies have a demonstration that they can do better than random test generation. Most research employs black box models, assuming a DUT is a black box where inputs can be controlled and outputs can be monitored. Optionally, some testing points can be observed. So the research does not seek to understand the behavior of a DUT. Instead, the focus is spent on reducing unnecessary tests. They employ various ML techniques to learn from the historical input and output observation data to tune the random test generators and eliminate tests that are not unlikely to be useful. In recent development in 31, reinforced learning (RL) based model is used to learn from a DUT's output and predict the most probable test for a cache controller. When the new reward given to the ML model is the FIFO depth, the experiments are able to learn from the historical result and hit the full target FIFO depth in several iterations, and while the random test generation based approach is struggling to hit more than one, hit more than one time. The paper does not further experiment with how it performs a more complex design where the reward targets are not easily definable. And reference 28 introduced an ML architecture with much finer granularity, where the ML model needs to be trained for every cover point. So a ternary classifier is employed to help decide if a task should be simulated, discarded, and used to retrain a model further. As a support vector machine, SVM, random forest, and deep natural network are experimented on a CPU design, each able to close 100% coverage with 3 times to 5 times fewer tests. Further experiment of FSM, non-FSM design have a demonstration 69% and 92% reduction compared to directed sequence generation. However, most of these research still suffer from the limitation of the statistical nature of ML. A more comprehensive review of the ML-based coverage directed test generation (CDG) in reference 32 gives an overview of several ML models and their experimental result. Bayesian network reference 41, genetic algorithms and genetic programming approaches, Markov models, data mining, and inductive, the logic programming area programs are or experiment with various degree of success. So in all approaches discussed, an ML model can make a prediction based on learning from historical data it has gathered, but has the minimal capability to predict the future, that is, which test might be more promising the option for hitting an uncovered test target. As this kind of information is not yet available, the best they can do is pick the tests that are most relevant of historical tests. A promising experiment conducted in 33 explored different approaches where the duty is regarded as a white box. The code is analyzed and converted to a control data flow graph CDFG, a gradient-based search on a trained graph natural network, as is used to generate a test for a predefined test target. The experiment is IBEX the V1 and V2, and a TPU achieved 74%, 73%, and 9% accurate at a coverage prediction when trained with 50% cover point. Several additional experiments also confirm that a gradient search method employed is insensitive to the GNN architecture. So you'll notice that due to the unavailability of the training data, most of these ML approaches only learn from each design without exploiting any prior knowledge from other similar designs. So 5 is bug analysis. Bug analysis aims to identify the potential bug, localize the code blocks containing them, and give fixed suggestions. The survey found the verification of the IC spend roughly the same amount of time as it does in a design, and that functional bugs contributed about to the 50% of the spins of the ASIC design. Therefore, it is critically important that these bugs can be identified and fixed in early functional verification stage. ML has been employed to help us developers detect bugs in a design and find bugs faster. So 3 progressive problems need to be solved to speed up the bug hunting in functional verification. Namely, a clustering of the bugs by their root causes, classifying their root causes, and a suggestion of fixes. Most research focuses on the first 2, with no research result on the third one available yet. In search conducted in reference 34, semi-structured simulation log files are used for bug analysis. It extracts 616 different features from metadata and message lines from the log file and undisclosed designs. The experiment of clustering achieved the adjusted mutual information (AMI) of 0.543 with k-means and agglomerative clustering, and 0.593 with the DVCON even after feature dimensionality reduction, far from the ideal clustering with the AMI achieved 1.0. Various classification algorithms were also tested to determine their accuracy and solving problem 2. All the algorithms, including random forest supporting vectors, classification SVC, decision tree, and logistic regression, k-neighbors in 9 ways are compared on their power to predict root causes. The best score was achieved by the random forest with 90.7% prediction accuracy and 0.913 F scores. Lafelle et al. Proposed to use the labeled data set from a code commit to train a gradient boosting as a model. where more than 100 features about authors and revisions and codes and projects were tested until 36 were selected for the algorithms. The experiment showed that it is possible to predict which commits are most likely to contain a buggy code and potentially reduce manual bug hunting time significantly. However, due to the relative simplicity of the ML techniques adopted, they are not able to train the ML models that can consider rich semantics in code or learn from historical bug fixes. Therefore, they cannot explain why and how the bugs occur, nor suggest revising the code to eliminate bugs automatically or semi-automatically. Okay, the section 3 is emerging ML target techniques and models applicable to functional verification. Significant breakthroughs in ML techniques, models, and algorithms that have been witnessed in recent years. Our paper found that very few of these emerging techniques are adopted by functional verification research, and we optimistically believe the greater success will be possible when they are used to tackle challenging problems in functional verification. The transformer-based large-scale ML models of the billions of parameters trained in the enormous amount of text corpus achieved near human or exceeding human level performance in various NL, natural language tasks. For example, the question answering, machine translation, text classification, attractive summarization, and others. The application of these research results in code analysis as a demonstration. These models create a potential and versatility. It has been demonstrated that these models can truly ingest a large corpus of training data, structure the learned knowledge, and provide easy accessibility. This capability is instrumental in static code analysis, requirement engineering, and coding assistance for several popular programming languages. Given enough training data, it is reasonable to believe these techniques can train ML models for various functional verification tasks. So until recently, it was hard to apply the ML to graph data due to the complexity of their structure. Graph neural network GNN advances have promised a new opportunity for functional verification. The research in reference 33 is converted design into a code and data flow graph, and which is further used to train a GNN to help prediction the coverage closure of a test. This kind of a web box approach promises previously unavailable insight into control and data flow in a design, which can guarantee direct test to fill potential coverage holes. Graphs cannot represent a rich relational and structural and semantic information encounters in verification. The rich information from training on an ML model on graphs can afford many new possible functional verification tasks, for example, bug hunting and coverage closure. The section 4 is the urgency of a large-scale verification open data set. Despite many encouraging research results in applied ML in functional verification, many challenges must be addressed to realize mature and large-scale success. Among them, the biggest challenge is unavailability of training data sets. Due to the lack of the large data set, much research has to settle for relatively primitive ML techniques that demand only small training sets with hundreds of samples. This situation has prevented advanced ML techniques and algorithms from being applied. So historically, IC designers consider the high-valued property of their respective owners. The design has the associated verification data, including verification plan, simulation settings and assertions, regression results, simulation logs, coverage data, trace files, and revisions, and their commits are also carefully guarded by their owners. If we were not bad enough, an internal survey that had indicated that a typical ML project will speed up to the 70% of the team's time on data preparation. It's also confirmed by the independent study that general data preparation, including data cleansing, reporting, visualization, takes 75% of the data professionals' time. This is the time that they spend before on any exploration of an original data, or original idea. So, the unavailability of quality training data and expensive data preparation is substantial hurdles for any time any team to research ML follow FE functional verification. It impedes the research advance and prevents research community from the learning from each other's success. After spending so much effort to time to accurate to their own data for the research, very few researchers that are ready to share their data, code, or ML models quickly publicly, making their research leisure hard to repeat and verified by other researchers. Consequently, it previously reduces the value of the ML research results. Standardization of the data format and active contribution to this kind of verification data set by the community will significantly accelerate the development of AI ML for the functional verification. And Siemens is actively working with different consortium and partners to make this happen. If there is anything to be learned from the ML in computer vision community, is that the abundance of the training data helps boost the research significantly. Published in 2009, ImageNet now contains 14,197,122 images in 21,841 categories of August 2022. And the unavailability has helped researchers invent the unthinkability of the ML models and compare at a comparable basis, which directly contribute to the practical application of deep learning. Challenges hosted by the Deep ImageNet help build a healthy community where the researchers can afford to focus on learning, inventing, and training their models instead of spending effort to accurate a small private data set. According to the 32, the ImageNet has changed the think of the ML community from the paying attending to models to paying attending to the data, which consequently helps define how models are developed. The opportunity of the FE also lies in such kind of open data sets. Our research GitHub, RISC-V, and open course conducted in May 2022 is also indicate the unlimited GIN and even fewer verification data available in public domain. The tables below summarizes our research result. We estimated that there are about 10 million lines of code and comments altogether. This scale is hardly comparable to millions of projects and billions of lines of source code in other population programming languages. Even more, the verification-related data are very sparse. Even it is possible to generate verification data from the set of source code. Tremendous effort must be invested by the individual research teams to decode the used data effectively due to the lack of the published and agreed standard upon common data schemes. Making these data unusable for ML tasks requires substantial effort to eliminate those with the restrictive licenses and those with a simple force, followed via further deep cleansing to ensure the quality and usability of the final data set. The paper did not identify any announced activities to curate open source verification data sets and making them available to the public. Table 2. Number of open source projects hosted in GitHub and RISC-V and of course. 5. Industrial perspective. In addition to the scarcity of the data, several other challenges must be addressed to be ensured the successful application of machine learning in functional verification. The model generalization is one of the most prominent challenges in many machine learning ML research results. An ML model's generalization capability measures how easy it is applied to the model trained from the training data to problems that are new problems that have never seen before. A model trained on data from specific types of design, coding styles in certain projects, and some niche types of the data might not perform well for other types of the designers, other coding styles with other project with other project or other types of data. The hard generalized research result will only have limited value in an industrial production environment. As cost of the training and imaging, these models can easily negate the value they bring to the solution. The model scalability is another challenge in applying these research results in a production environment. A model might perform well for a relatively simple design. However, there is no guarantee it would work equally well when applied to a large-scale design with billions of RTL gates with coded multiple development teams spanning multiple continents. To benefit from these models, additional investment in further model compression, additional computing resources, for example, ML accelerator and establishing ML ops might be inevitable. The decision to investment in this effort must be balanced against the expected return from applying ML, which is not yet evident in many cases. The third challenge is related to the data governance in ML applications and real-world applications. The owner of the dataset used to train ML models, the FV tool developers and a tool user might belong to different organizations. So in combination of this distribution of computing power and availability of the ML expertise, they may jointly dictate the selection of ML models. For example, a user who cannot divulge her data of her organization and has no ML infrastructure may not be able to use an ML model that requires much computing for training or her data to achieve optimal performance. Alternatively, a functional verification tool developed with a mature MLOps workflow, cloud infrastructure, and knowledge may be able to offer attractive functional verification tools hosted in a cloud with easier accessible RESTful APIs the user may integrate into their FB workflow. So the summary. Abundant data available along a design lifecycle. ML is one of the best tools to extract values from the data for functional verification. This paper has presented a comprehensive survey of how ML may help address almost every aspect of functional verification. These typical applications, their state-of-the-art achievements are summarized and discussed. Despite the diverse ML techniques applied, and most researchers still employs the primitive ML techniques and is restricted by the scale of the training data. It's not dissimilar to an early days of ML applications in many advanced domains and prompt the ML applications in functional verification are still in their early days. Many advanced techniques and models are yet to be applied to exploit ML's potential fully. So much semantic, rational, and structural information has not been fully utilized in today's ML applications. So the working experience and review of the many research results has indicated the application of the ML in functional verification cannot advance at much faster pace without a substantial quality data set being made available. The paper calls for Apple to build a more extensive data set in training more complex the machine learning models. Such data will afford the functional verification community to make research results more comparable, repeatable, and credible. The paper also presented in other critical challenges to be overcome the released potential of the ML in functional verification and generalizability, scalability, and data governance. The other three main challenges every industrial researcher has to consider applying the ML in a real-world production. Recognizing their implication will also help identify the suitable ML models applicable to many possible diverse use cases. The paper's author's optimistic and functional verification is intrinsically a data analytic problems in ML is powerful to extract value from the abundance of the functional verification data. We look forward to seeing more contribution from community developing quality data sets and applying to the advanced ML techniques and also successfully adopting the ML in functional verification tools. Okay, thank you. There are so many references 1 to 12. Thank you. Not 12, not 20, 42. Okay, today, thank you for your time and see you next time.